Hey guys, we're here today to have our last video of the semester on our lesson for graphing rational expressions and how to find key features for these expressions. So this is what we've been talking about in our last few videos, finding excluded values, factoring, simplifying, and we're going to see how that all comes together here to help us to find three key features of different types of these expressions that are fractions involving variables. So we have two examples on the board. I'm going to walk through both of them and show how once we have done the steps that we've taken in the last several of our videos, factoring, finding excluded values, and then simplifying by canceling, how that will enable us to find three different key features for these types of expressions and functions. So let's start with the example on the left. If we were to factor this, we would want to use the box method for the numerator, and we could do that for the denominator as well. We'd be thinking about what times what is 2x squared in our numerator, and that would be 2x times x. And then think about what times what is negative 5, but also adds to give positive 9x. So you have two possibilities here. Two things that could multiply to give negative 5. The one that you're going to want to choose after testing a bit will be positive 5 times negative 1 in this order. Okay? Because in this case, 2x times 5 is 10x, and x times negative 1 is negative 1x. Only 10 minus 1 will give us 9. Okay? That middle term, b. And then if we want to factor our denominator, so we've already factored the numerator, right? This is just the same thing as 2x minus 1 times x plus 5. If we want to factor our denominator, you could use the box method again, or perfect square factoring, which is a pattern, something plus something times something minus something. And both of these terms can be square rooted evenly, right? Square root of x squared, x times x is x squared. Square root of 25, 5 times 5 is 25, or in this case, 5 times negative 5 is negative 25. 5 minus 5 will cancel out any middle term you have. Factor first, then find excluded values second. Okay. Those are the numbers, if you remember our last videos, that x cannot equal. Okay, remember, you can never divide by 0. So x itself can be 0, because 0 plus 5 is 5. I can divide by 5. But I cannot divide by a 0. So negative 5 plus 5 would be 0. X cannot be negative 5. Likewise, 5 minus 5 would be 0. Can't divide by 0. X cannot be positive 5. So two numbers here, two variables in our denominator, both with different parentheses. Two numbers specifically that x cannot be. And only now are we able to cancel top and bottom. Parentheses that look the same, x plus 5 top and bottom. We're left with 2x minus 1 over x minus 5. Okay. Y equals this, or f of x equals this. You have that equation and function now written. This is what we've done so far in our lessons. So today we're going to talk about how to find something called the horizontal asymptote. Then we'll move on to vertical asymptote, and finally a hole. Now, a horizontal asymptote, we're going to create a horizontal line, and the graph will approach this horizontal line from both sides. And in this case, the way that you find that is by looking at the first term top and bottom. Do they have the same exponent, or is one larger than the other? Okay. First term on top, the degree here is a 2, as well as on the bottom. So in this case, to find our horizontal asymptote, write this down here. To find our horizontal asymptote, we see that we have equal degrees, top and bottom. So all we need to do is divide these terms. 2x squared over x squared gives us y equals 0. That is going to be our horizontal, sorry, not 0, 2. Excuse me. Clearly the variables will cancel out. X squared over x squared. 2 divided by invisible 1 is 2, not 0. So that means we're going to have an invisible dotted line that we create that the graph is going to approach when we graph this problem. Towards the right side, it'll approach y equals 2. Right, it's crossing the y-axis at y equals 2 here. And towards the left side of the page as well, the graph will also approach y equals 2. For a vertical asymptote, okay, how do we find a vertical asymptote? We're going to look at an excluded value. Okay. Which excluded value are we going to look at? The one that associates with the variable left over after step 3 in our denominator. So what's the excluded value from this denominator? It's a 5. Okay. In this case, our vertical asymptote will be x equals 5. Now you might find that a bit counterintuitive, right? Wait a minute, I thought x could not equal 5. Well, the vertical asymptote is this blue line, okay? It's way over here. This is x equals 5, this blue line. This is where the graph will not touch. So when we make our graph, it will never cross this invisible dotted line, this barrier, okay? So actually, x cannot equal 5, right? Because it never touches that dotted line. The graph is actually going to look something like this. And like that. It'll get close to your asymptotes, but it never actually crosses them in this case, especially not the vertical asymptote, right? We said x cannot be positive 5. So the graph's never going to cross that invisible barrier, that invisible dotted line, up and down, crossing the x-axis at positive 5. And lastly, that takes us to what is a hole. This is our last key feature we're going to talk about. Okay. Using this as an example, then we'll do one more example after this. What is a hole? Now, if you recall, we had more than one excluded value, right? We actually had 2. Positive 5 was one of our excluded values, and that went with the thing that did not cancel, right? The parentheses x minus 5 that did not cancel. That is our vertical asymptote. Our hole is going to associate with the excluded value that did have a parentheses that canceled. X plus 5 canceled. What was the excluded value we found for this? Negative 5. That's part of our hole. Okay. I say a part because a hole always has 2 components. It's a coordinate point, x comma y. Okay? This is going to be somewhere a coordinate point that the graph does not exist. So, at negative 5 comma something, the graph will skip over this point. And if I go 1, 2, 3, 4, 5, the graph is actually going to skip over this point. It'll be an empty space because the graph can't be at negative 5 comma something. Now, what is that y coordinate that goes along with our x coordinate? How do we find that? What we'll do is we'll take negative 5 and plug it into whatever's left over in step 3 after you canceled out that parentheses. Okay? So what is left over now? Well, if I plug in negative 5 into both of my variables, x on top, x on bottom, what I get is 2 times negative 5 minus 1 over negative 5 minus 5. 2 times negative 5 is negative 10, again, minus 1. Negative 5 minus 5. This is going to be negative 11 over negative 10, and negative over negative is a positive. This turns out to be a fraction. It's like 1.1 if you divide that in a calculator. So at negative 5, comma, 1.1 or 11 over 10, that's the coordinate point that the graph skips over. It can't exist there, right? It's an excluded value. Why is it an excluded value? We found that in step 2 already. We can't divide by 0. Even from a parentheses that cancels out, we can find an excluded value. A hole comes from a parentheses that cancels involving a variable. Okay, so that's one example of finding asymptotes and holes. I do want to do one more example. because I think the more examples we do, the better it will be to understand these key features. Now what I'll point out is that actually for our horizontal asymptote, we don't have to do any of the first three steps. We could at the very beginning, x squared over 3x, right? Don't need to factor to look at our first terms on top and bottom. What you'll notice here is that the degree on top, that 2 is larger than the degree on bottom, which is 1. If the degree on top is larger, that tells us we actually won't have a horizontal asymptote. There won't be one, okay? The graph can exist everywhere towards the left and right. In fact, the line that we'll see for this graph in particular will be diagonal, okay? Because the graph is diagonal all the way left and right, it never tapers off, it never flattens out. In other words, like our graph did earlier where it approached the blue dotted line horizontally for our previous graph. So there is no horizontal asymptote for this problem. We're going to keep that in mind. Okay. And go ahead and start to, and by the way, if the degree on bottom was larger, let's flip this. Let's say that we had a different problem and it was like 3x over x squared. Okay, so clearly that's different than what we have. But if you did have something like this, what will that look like? You'll have a horizontal asymptote after all, and it will be at y equals 0 on the x-axis. Okay, the graph will flatten out towards 0, left and right, only if the degree on bottom is larger than the top. So just wanted to mention that. But in this case, clearly the top is larger than the bottom instead. No horizontal asymptote. So now we can go ahead and try to factor. Do our usual steps when approaching a rational expression. Factoring this, box method on top, x times x is x squared. 3 times 4 is 12, and 3 plus 4 is 7. So this multiplies out to give your original numerator. For the bottom, we look at a GCF. We can divide both 3x and 9 by a 3. It's our greatest common factor. Divide by 3, what's left over? X plus 3. 3 times x, 3x. 3 plus 3 is 9. This is step 1. Okay, factor. Then look for excluded values. Step 2, what can x not equal? Again, you can't divide by 0, but x can equal 0 because 0 plus 3 is 3. You can divide by 3. You cannot have x equal negative 3. Negative 3 plus 3 would be 0. Or if you look back to the original problem, 3 times negative 3 is negative 9, and negative 9 plus 9 would be 0. Again, excluded, not allowed. Only now can you cancel top and bottom, simplify. What's left over? X plus 4 divided by 3, y equals this, or f of x equals this. Simplified expression with this excluded value. Now, if we're looking for other information like a vertical asymptote, remember, it occurs when you have factors in a denominator that don't cancel. So in this case, do we have a variable left over in our denominator at the end of this problem? No, right? For our previous example, when we canceled, we had a variable left over in our denominator, but not here. So there's actually not only not a horizontal asymptote, there's no vertical asymptote either. You can only have a vertical asymptote if you have a variable left over in your denominator after step 3, after you simplify by canceling. Here, it was positive 5 because 5 minus 5 is 0. Excluded value, vertical asymptote, dotted line, the graph will never cross. Not here. No variable in our denominator. So the only thing that we can have is a hole in this graph. A coordinate point the graph will skip over, x comma y. And in this case, that's where we're going to see our excluded value come into play. Remember, this came from parentheses that canceled, right? X cannot be -3. Holes always come from parentheses that cancel. X cannot be -3. -3 comma what? Well, we'll take that -3, plug it into x, see what we get. That'd be -3 plus 4 divided by 3. -3 plus 4 is 1 divided by 3. That is our hole. So apparently at -3 comma positive 1/3, and if you graph this on Desmos, it will look something like this. Okay. There's a hole there. The graph does not exist. It exists everywhere else except for that coordinate point that it skips over. X cannot be that value. That wraps up our lesson on key features of rational functions and expressions. That wraps up our semester. So we do have some final exams to get to. Come to me if you need help on those. And I hope this video and all the preceding ones have helped you this semester. Good luck, guys.